Hello everyone. In this video, we are going to talk about force vibrations of single DOF systems when the excitation force is an arbitrary force. Because you watched my previous video, you saw that I consider this force to be a harmonic force and I could easily find the response of the system, in this case X, of the mass spring damper system or any other single DOF system. You see that the response has two parts, a transient or a homogeneous part actually, and a particular part. The particular part will take the form of that harmonic, and the homogeneous part depends on the value of the damping factor. But what if this F is any other kind of force? Not every force you see in real life is harmonic. Sometimes the force could be, for instance, a pulse, a shock, right? And shock is basically similar to a pulse with bigger magnitude, a smaller duration. It could be a sawtooth function. So the kind of pulse that you get could be this. It could be a simple bump, for instance, right? When you go over a bump, the bump is not it kind of looks like half of a sine wave, correct? But the sine wave does not go forever, it stops. So when you're dealing with this kind of arbitrary force, how would you find the response of the system? And the answer is, if the system is linear, like the systems we are looking at right now, the best way to do it, if you want to find analytic solution, is by Laplace transform. And that is what I'm going to discuss in this video. If the equations are nonlinear and there is no analytic solution, the best way to do it is a numerical solution. So you solve the governing ODE numerically with any numerical solver, with any algorithm for numerically solving ODEs, including the Euler's method, which is the simplest one, or more advanced methods like the Runge-Kutta method. Another way that you can handle it is to find an approximate analytic solution is to apply Fourier transform on that f of t and convert that f of t into a bunch of sines and cosines. And then for each one of those sines and cosines, since they are harmonic, you can find an analytic solution based on our previous videos. And then since the system is linear, the total solution is going to be sum of those individual solutions. Again, this superposition, which is adding those individual responses together, only works when the system is linear. If the system is nonlinear, you cannot use superposition. And why does it give you an approximate analytic solution? The reason is when you do a Fourier series, you're approximating this function by what? By, for instance, a constant a naught over 2 plus a bunch of basically something like ai times cosine of something, correct? I goes from 1 to infinity, and then plus a bunch of sine terms like bi sine of increasing frequency. The thing is, these summations go to infinity. There are infinitely many terms. You cannot keep adding infinitely many terms. So what you do is you literally only look at the first few dominant frequencies and you stop here at some n. You don't go to infinity. You only use those that have the highest contributions to the response. And for that reason, you're approximating, okay? So you can use Fourier transform as well. If you want to know more about Fourier transform of different functions, I have a video under my playlist, Engineering Mathematics, but for your convenience, I'm going to copy that into my Vibrations playlist. So there you can see more about Fourier series. I also have a video about Laplace transform under my Controls playlist. Again, for your convenience, I'm going to copy that into the same playlist, into the Vibrations playlist. And I have videos on numerical solution of differential equations, including the one in Vibrations, and that talks about Euler method and Runge-Kutta. Again, this one is under Engineering Mathematics. I will copy this one as well for you under playlist Vibrations. I want you to have a good full playlist that you can study alone without going to my other playlist when you go to the Vibration. And as I promised you, I also copied for you the video regarding the Lagrangian method, because most of the time you see here I'm using Newton method, but since you can derive these ODEs also using energy or Lagrangian methods, I copied the video I have, one of the videos I have on Lagrangian, I copied it from my dynamics playlist into vibrations. So now wherever you go to the vibrations playlist, guess what? You have all of those required videos. So here, as promised, under vibrations playlist, you see Lagrangian method, Fourier series, numerical solution of ODEs, and review of Laplace transform. So I have copied all of this from my other playlist here. So when you go to the vibrations playlist, again, it's a complete playlist. Hopefully that will help you. So here, since we want analytic solution and we want a full analytic solution, not approximate, we are going to use Laplace transform. So let's say here I have this mass spring damper system and the input to the system is a pulse, okay, for 1 second with a magnitude of 1 Newton. That's all I do. It's like a short kind of push with a constant force and then let go, correct? So if I give it a little bit force and then cut the force, what kind of response do I get? Well, of course, you expect the X to increase because initially there is no damping force or spring force. So the X will increase, mass moves to the right. But then as those forces start to build up, they will push back. And when this force goes away after 1 second, those forces still exist. So depending on and between 0 and 1, depending on which one of them is stronger, you might stop or you might keep moving. But after 1 second, there is no force here. Those forces are there. So it is going to move back. So you're going to see a little bit of oscillation, but there is damping in the system and there is no more energy injected into the system after 1 second. Therefore, that damper will very fast dissipate the energy of the system and the vibration of the system will stop. So you should see some short duration vibrations, and that is kind of what logic and what common sense say. Now let's see if that's the reality, if we solve for it and if we simulate it in MATLAB. So here I go with some numerical numbers, C10, K100, M1, and I go with 0.1 meters initial position and starting from rest. Now, the way that you want to model this pulse is by subtracting 2 unit step functions. One that starts right at time t0, the other one with the delay, it starts at time 1. If you subtract these two, you should get a pulse, right? So here I plot those 2 functions for you. So if I plot both of those functions versus time for you, and this is 1 second and this is 1. So the first function starts at time 0 and then go to 1 and keeps going like that. That is unit step function. Okay, so this is US of t. And the second function, it is 0 until 1. At 1, it goes to 1 and it keeps going. So that is US with 1 second delay. Well, of course, if we subtract these two, what do we get? For the first second, US is 1, US of t minus 1 is 0, so you get a 1. After that, since they are both 1, the subtraction will go to 0. So if you subtract, the subtraction will be what? Will be a 1 here, and then after that, all 0, and before that, all 0. So clearly, it is going to be a pulse like the one I showed you. And in applying the Laplace transform to unit step function is very easy. As you know, this Laplace of step function is simply 1 over s, and this one is 1 over s times e to the negative s. And negative s times this amount of delay, which is 1 in this case. So I have the Laplace of these, and that's why I can write my function in terms of those. And since Laplace is a linear operator, so the Laplace of f is going to be simply the subtraction of these two. So the governing equation for this system is mx double dot plus cx dot plus kx equals f, and f is us minus us of t minus 1. Now here I'm going to apply Laplace to both sides. And if you go back and look at the tables of Laplace transform, Laplace of x double dot is going to be s squared Laplace of x minus the x function here, the actual function, the time function in time 0, so this value, times s minus x dot at 0. And then for x dot, the Laplace of x dot is s times x of s minus x at time 0. For this part is k times x, and then the Laplace of the right-hand side is that. Now what? Now if you look, some of these terms here in this second line, they have x of s in them. Which ones? This one does, this one does, and this one does. So I factor x of s between those, and if I do that, then I will get this. These guys, if I plug in numbers, anything that does not have x of s, I take it to the other side. So I take this guy here, this one, and this one. Now x dot is 0 in this case, but these other terms, I'll take them to the right-hand side. Okay, and those are these guys, a 0.1s and a 0.1. I take them to the other side. Now if I factor x of s between all of these, x of s, basically the coefficient of x of s is going to be this denominator here. Okay, and now of course you have to pay attention, although this is 0.1, but it's multiplied by a 10, so I get a 1 on the other side. So I get a 0.1 times s plus 1. I will get those two terms on the right-hand side. On this left-hand side, I will get m is 1, so I get s squared, plus what? C is 10, so plus 10s, so s squared plus 10s, plus k, which is 100, exactly this one, times x is equal to the right-hand side. So I divide both sides by the coefficient of x of s, and there we go. This is my Laplace of the solution. So remember, the goal is to find x of t. But now I found the Laplace of x of t so far. I solved for Laplace of x of t. And the good thing about Laplace transform is it converts your differential equation into what kind of equation? What kind of equation is this? You're right. Here, if I wanted to solve for x of s, it's just algebra. So this one here is an algebraic equation, while this original one was a differential equation. That's the power of Laplace transform. Converts a differential equation into an algebraic, which you can easily solve. Now that you got x of s, you can apply Laplace inverse and get what? X of t. Now, applying Laplace inverse here is, it needs some extra work here. It's not as simple. You might say, well, can I just go and look at the tables of Laplace transform and then find some function, the Laplace of which is this big guy here? No, there is no function in those tables that has this big of a guy as its Laplace. So you have to break this big rational function into smaller terms, into its constituent terms. So to do that, we need to apply partial fraction expansion, PFE. So we break this denominator into its terms. Now, this denominator, that is a quadratic term, has no real roots. Actually, you can write it like this, s plus 5 squared plus 75, and you clearly see that the roots of this are complex numbers. So if you find the roots of that, s1 and 2, they're what? They are negative 5 plus minus square root 75 times I. So this one has no real roots, it's just complex roots. And when there are complex roots, that's an indication of sine and cosine. So what you need to do is to write it as a combination of basically this guy here, this term that is squared, it has to be there, and the other one should be the square root of this in the numerator. This one corresponds to a cosine, this one corresponds to a sine. Okay? Cosine of what and sine of what? Cosine and sine of this, the square root of that, basically this number, times t. So the frequency here is square root of 75 times t for both sine and cosine. Now remember that the Laplace of sine of a t is what? If you remember from the tables, this is a over s squared plus a squared. Okay? And the Laplace of cosine of a t is s over s squared plus a squared. But here you don't have s in the numerator and denominator, you have s plus 5. So you need to use another thing from Laplace transform, and that was Laplace of e to the negative at f of t is f of s plus a, correct? Or in this case, s minus, yeah. If it's positive, negative a, then it is going to be like this. Okay, so clearly because it's s plus 5, it means that although you will have sine and cosine, but an exponential of negative 5t should be multiplied by them. Therefore, you have decayed sine and cosine, basically underdamped response. So here, this portion of your solution is the underdamped response, and it's the result of what? What is this part coming from? If you look at this part, it is coming from your x of 0. It's this x of 0 that was 0.1. This one is the reason for this part of the solution, because remember, when you plugged in 0.1, that x dot was 0, you took them to the right-hand side, you get this. And when you broke that part into two components of it, look. Sorry, I need to do a little bit cleaning. It's getting out of control here. So here, this guy is broken down into these two. So those two and their Laplace inverse are just due to this initial condition. So what kind of solution is this? You are right. Remember, the response due to initial condition here, this whole portion is basically your xh of t. This is that homogeneous solution, and in this case is underdamped. Okay, it is what? It is underdamped response. Good. And clearly you can find zeta for it and omega n for it. You clearly see that zeta omega n is 5, and omega n square root 1 minus zeta is square root 75. So this guy here is your omega d, which is like this. And this 5 here is your sigma, which is zeta omega n. Okay? So this is your homogeneous solution, and of course, as time goes a little bit large, those exponentials make everything go to 0. Now, the part that is due to the external force, look, this is the Laplace of the external force divided by this characteristic polynomial of the system. So this portion, whatever it is, when you apply Laplace inverse to it, the result of that will be the particular solution. And for this part, this is the Laplace inverse, all of this. Therefore, this guy is xp of t. So your particular solution is of this format. Okay? Now, how does that work? Again, here you have to break this portion into a bunch of sines and cosines, or simple linear terms. There is no linear term here because none of the roots of this polynomial in the denominator is a real number. So here I had to break it, and there is one difference here that you need to pay attention to. What is the difference between the one on the left and the one on the right? The difference is this. Here, they both share S, so S will come here in the denominator, so your denominator for this guy is going to be a third order. So when you break it down, when you break that down, you're going to have three terms with partial fraction expansion. One of them is going to be something over S, one of them is going to be a cosine term, one of them is going to be a sine term. Okay? And once you get 1 over S, remember 1 over S, the Laplace inverse of that is step function, and these guys are the cosine and sine. And this is for this portion, and then the part that this whole thing is multiplied by e to the negative s based on what we know, that Laplace of f of t minus delay is e to the negative ds times f of s. We know that whenever an exponential we have in the Laplace domain, in the time domain, it translates to a delay. Therefore, you see the bottom portion here is the same as the top portion, except wherever you had t, now you replace it with t minus 1. Why minus 1? Because the power of this s here is 1, negative 1 times s. Okay, so that is your particular solution. This is your homogeneous solution. Now, what happens to these solutions as time gets bigger and bigger? What do you expect the steady state response of the system be? So we want to see what happens when time goes to infinity. What kind of response would I get from x of t? So here we are going to clean it up a little bit, and let's look at each and every one of these terms, see if any of them will survive or they will all go to 0. Okay? So what do? Let's take a limit. T goes to infinity. So any negative exponential will clearly go to 0. Which ones? Well, if you look, this goes to 0, this goes to 0, this goes to 0, this goes to 0. This one goes to 0, this one goes to 0. So everything goes to 0 except 100 us of t minus us of t minus 1. This is the kind of thing that your system will converge to. But when t gets bigger and bigger, if you remember the two pulses that I showed for you, when time gets anything bigger than 1, both of these signals, when t is bigger than 1, both of them are equal to 1. Okay, as you can see, they are both equal to 1. Therefore, both of them are 1, so really your signal x of t should converge to 0. And that's what we physically expect. We give it an initial kick to move. So a little bit of energy, a little bit of momentum is all we inject into the system by applying this force only for 1 second. Once we let it go, the damper will dissipate the energy very fast, and I expect that the system will stop. Now, is that the case? If I numerically solve this system in MATLAB Simulink, would I see the same behavior? The answer is yes. So here, look, I made the system for you, mass spring damper system. And here are the initial conditions, right? So x dot is 0 and x of 0 is 0.1. These are values for kc and 1 over m. This is sum of the forces divided by m. That's your acceleration. And here I have a manual switch. If I keep it up, the force that I'm sending into the system is the difference between us of t, the step function, where the step time, that's the delay, is 0, the final time is 1, so that's us of t. This one, the step time is 1. Step time is when the signal starts. That's the amount of delay. You see, this one is 1. So this is us of t minus 1. And the final value for both of them is 1. So when I subtract, I should get a pulse here. That pulse goes to the system, and I can see x here. I can see the pulse here. Now, this is for next example. Okay, so let's go ahead and run it, and I run it for 20 seconds. So first, let's confirm that the input is actually a pulse. So we are going to monitor this, and we also going to monitor x. There we go. Look, You see, it is 1 Newton only for what? For 1 second, and after that it goes to 0. So I indeed have a pulse. And let's look at X. There we go. You see, it starts from 0.1 with initial slope of 0. It goes down. It has a little bit of oscillation. And then after about 2 seconds, all of those exponential negative 5t's are now literally exponential negative 10. So they will all go to 0. So after about 2 seconds or so, all the energy of the system is damped by the damper. And the reason that here you don't have a clean peak and you have this extra kind of twist in that signal is because the effect of the initial condition is not all 0. So there is a little bit of transient response here still available, but as time goes on, the transient and the particular solution, all of them go to 0. Therefore, your energy of the system is all gone. That's it. Yes? Just as simple as that. Now you might say, well, what if I get rid of one of these step functions? What would you get? Right now, it's us of t minus 0, literally. So what you are giving to the system is a constant force of 1 Newton to the right side. Okay, so let's see what happens if instead of a pulse, you give it a constant force. First, let's confirm that this is the case. You see, it stays at 1 and goes forever for 1. It never drops down to 0. Now let's look at the behavior of the system. So this is the behavior. Now look. Again, it goes down the oscillation. There is a little bit oscillation. When the oscillation goes away, what kind of value would you get in this system? The value that you will get in this system is 0.01. You see, it's right between 0 and 0.2. It converges to a constant value of 0.01. Is that realistic? Well, let's go back and look at the system. When the system goes to steady state, if the system steady state behavior is constant, so if x of steady state is constant, if the system converges to a constant, what does it mean about x dot and x double dot? Well, you're right. They are both equal to 0, correct? Of course, with different units, but they are both 0. Yep. So go back and look at the original ODE. If x dot and double dot are 0, right? And this guy is also 0, and this one is 1, correct? You get kx steady state equals 1, and k was how much? 100, right? So how much do you expect x steady state to be? 1 over 100, which is exactly 0.01. And that's exactly what I got. You see? Very obvious. So you see that the theory works and the Laplace transform is beautifully doing its job. Now you might wonder, what if I had a triangular pulse like this, a sawtooth, you might call. If my pulse was like that, how do I apply the same Laplace that I learned and get the response? Well, the answer is, again, similar. Can you write this f in terms of primitive functions like step function or ramp, in this case, a ramp function? Ramp is a function that starts at, so if this is f versus time, it's just f of t equal t. This is called a ramp function, a linear function. Can you make that triangle with the ramp function? If you do, you know that the Laplace of the ramp function is 1 over s squared. So we should be able to do that. Well, can I do it? The answer is yes, but here, in order to make it happen, you need 3 of your primitive functions to make it happen. All of them are ramp functions, but there are delays. The first one has no delay, the second one has 1 second, the third one has 2 seconds, and they have different weights. The first one has weight 1, the last one has weight 1, the middle one has weight -2. If you combine these 3, you should be able to get what? To get the rectangular pulse. And let me tell you how it is happening. So the first one is the ramp function starting at t of 0. The fact that I multiplied by us of t is to show the delay for it. So this one is like a 1. It has no effect. So the first one starts at time 0 with the slope 1. So this is what you get for the first one. It goes like this. Now, when you reach to 1, what would you need to do? You have to stop this growth because it is going up. You have to bring it back down. Yes? Is that right? But the thing is, the slope of this is positive t. The slope of this is negative t. So you have to go from positive t to negative t. So you have to subtract 2t from this to get to this one. That's why you subtract a 2t and you start that signal at 1 second. So at t of 1, you bring in a function with a slope of negative 2t. So when you combine it with that first one, after this point, the slope of the line becomes negative 1t. Now, what happens when you combine these two? The problem is, for the time between 1 and 2, it does the job, it brings the signal down, but after t of 2 seconds from this point onward, what's going to happen? After this point, you have to bring the slope back to 0 because you want to not continue this, you want to go back to 0. It's a pulse. So now what? After this point, you have to go from negative t now to slope of 0. So you need to add a positive t to this to make the slope 0. That's why you add a positive t. But that starts at time t of 2. Therefore, you add those, and guess what? You made your signal. Do you see that? How easy it is to make a rectangular pulse. Okay, now if I have that, the Laplace transform of the left-hand side is exactly the same. So if I go back and show you, the Laplace of the left-hand side will exactly be this again. The right-hand side will be different. The right-hand side, if I want to get the Laplace of the right-hand side, what's the Laplace? For this one, as I said, is 1 over s squared. For this one, it is going to be negative 2 over s squared, but there is a delay, so it's going to be e to the negative s. And for this one, it is going to be 1 again, because the coefficient is 1 over s squared, but there is a delay, so times e to the negative 2s. So this is the Laplace of this forcing function. The left-hand side is the same. Again, what you do is you solve for x of s. You find some huge thing here where this portion is the homogeneous part. This portion is this guy here. And then you have the same s squared plus 10s plus 100. And this part, if you remember, it was 0.1 s plus 1. So let me write it. And this portion is exactly what we found. So it's s squared, and then 1 minus 2 exponential negative s plus exponential negative 2s. Okay, so if you solve for x of s, this is x of s. Now again, you do partial fraction expansion, and you'll see that this portion will give you the homogeneous solution, which is going to be the same as last time. This portion here is going to give you the particular solution. So this one, when you apply Laplace inverse, will give you xp of t. This portion, when you apply Laplace inverse, it will give you xh of t. That's all you need to do. And that's your analytical solution. Now here, since you have s squared times this in the denominator for the x of p, not only you will get this damped sine and cosine, you will also get t, okay, and you will also get constants like 1. Okay, so if you give it a ramp, the response is going to be more like a ramp as well. Okay, but only for some time. After that, because the energy of the system, the injection of energy of the system stops at T of 2, after T of 2, the damping will dissipate this initial momentum and will make the system stop. So you might say, well, show me that with numerical solution. There we go. These are those ramp functions. So start time 0, slope 1. Slope -2, start time 1. Slope 1, start time 2. I add them, I get the pulse, and I send it to the system. Now to make this guy go to the system, I double click on this manual switch. So now this one goes through. And again, let's go ahead and run. First, let's check. There we go. You see? It is a pulse for 2 seconds and the magnitude is 1 in the middle. So it is really a rectangular pulse, and let's look at the response. There we go. Okay, so I get some response, and then after 2.5 seconds, 3 seconds, the energy of the system will damp out, and that's it. Now you might say, if you give a ramp to the system and get rid of these other ones, so just make the input a pure ramp, not a pulse. So the input to the system constantly increases in magnitude. What kind of response would you expect? Look here. Now you see that the input is increasing linearly, constant, with the slope of 1. And if you look at the response of the system, it also acts like a ramp as well. Okay? Now, of course, the magnitude of it, the slope of this one is not going to be 1. The slope of this, if you look in 20 seconds, it only goes to 0.2. So the slope here is something like what? Like 0.01. The slope is like 0.01, not 1. The slope is 0.01. But it is showing the ramp behavior. Now, where would you get the slope of 0.01 from? Let's see if you remember what I just explained for you. Where would you get that 0.01 from? Excellent, you are right. That comes from this K. This K will bring down the magnitude of input by 100 in the steady state scenario. This time, in the steady state scenario, your X is varying linearly with time. So it's like A times T plus B. So X double dot is 0 in this case. So this term is only 0. And this one is just like T. So the solution is Cx dot plus Kx in the steady state is going to be equal to T. Okay, now this K is 100 and this C is 10. Now, if your steady state behavior is like this, your X dot is simply going to be A. So what would you get? You will get 10 times A plus 100 times X, which is AT plus B. This is equivalent to simply T. And I assume from here you can find a solution, because if you set the T terms equal, you see that 100 should be equal to 1, and then 10A plus 100B should be 0. So you see that your slope A is what? 1 over 100. And if you plug it here, that is going to give you a 0.1 divided by B. B is going to be negative 1000. Okay, so your behavior should be like 0.01T minus 0.001. That's the kind of steady state response that you should expect. And that was exactly that line that you saw here in X of T. This guy here. Of course, not this one because I removed it, but If I put those back to 0, that is exactly the kind of response that you would expect, right? Here. You see that line does not exactly pass through origin. It has a little bit offset. And that is that 0.001. Okay, so, and you can pass any other function you want. Just as the last example, I don't want to solve it completely, but if the input was a bump, so most of the bumps that you see outside on the streets are kind of like a half sine wave, correct? So they are kind of like this. So this length is L, this magnitude is A, and let's say you can say this is kind of like a sine wave. So what kind of function is that? If this is f of t, what can I say about this f of t? Well, if it was a full sine wave like this, you can write it as a times what? Sine of omega t. Omega is what? Omega is 2 pi over t. In this case, t is 2 times L, correct? So for t, I write as 2L. Therefore, it's going to be pi over L. So that's my function, correct? You clearly see if I plug in 0, it's 0. If I plug in pi in here, L in here, sine of pi is going to be back to 0. So this is my function if it was a full sine wave and repeating itself. But the thing is, this is not repeating itself. It stops right here. So what can I do? You're right. Although this one should go like this and continue, if I add this sine wave, the same sine wave, but with a delay like this. If I add this sine wave to it, so add the blue signal to the red signal. Red signal starts at time 0. The blue signal starts at time t equal L. Starts here. What is this signal? You are right. That is a times sine of pi L times t minus L. And to make it more controls-like or vibrations-like, I would multiply it by a US of t minus L to show that the delay is starting, the time starts after t equal L. Okay, if I just add that to it, would that do the job? So I say my function is this. Would this create a bump for me? Well, just try it. Between 0 to L, this guy is 0, so you will exactly get that. Now, let's go, for instance, for what? For somewhere here. That is 3L over 2. So I plug in 3L over 2 in both of them. See what you get. Well, US of anything positive is 1, so that whole thing is 1. Here you get L over 2 for this whole argument, and L over 2 and L you would cancel, you get pi over 2. This here you would get what? You would get 3 pi over 2. And what's sine of 3 pi over 2? Well, you're right, it's negative 1. So this whole thing will be negative a, and this one, sine of pi over 2 is 1, so it's going to be positive a. And add them together, you are going to get a 0 after this. And you add it at any other point, it will also be 0. So what you will get is, basically, you will get a bump between 0 to L, and then after that, you would get a 0 by adding these two sine, a sine and a sine with delay. That will give you exactly a bump. And you can simulate a bump as well. So here I can simply go back and I can add a bump if you want in addition, right, to all of this, and I can simulate that as well. So here I decided to add a bump for you. So here is that sine wave. This is the sine wave multiplied by the step function to limit it to only have non-zero values after so much. The L that I used here is 2. And so you can see that my sine wave has a frequency of pi over 2, because remember, the frequency, as I said, is pi over L. And if L is 2, the frequency of my signal should be pi over 2, which it is. Now, if you look, this original one has a frequency, a phase of 0, but this next one that starts with the delay, the phase of it is pi. Why pi? Because pi means it's 180 degrees back in phase, and that's exactly what it is, half of the period. So the phase of this signal with respect to this one is basically 180 degrees. And if I don't multiply this step function, which is starting at 2, you might say, what's going to happen? Well, if I don't do that and simply add those two together, what do you expect to happen? Well, because there is no step, that sine function will also have values before time of 2. So you will get pure 0. You're just adding a sine wave and the 180 phase shifted version of the sine wave, you will get 0 all the time. I want this blue wave to start after time of 2. Therefore, because the sine wave itself does not start at time of 2. But if I multiply it by the step function, which is just 0 before 2 and then jumps to 1, now I suppress this portion of this blue curve that is before time of 2. Okay, and I do that with the product. So now look here, right? That's my bump, magnitude 1 for 2 seconds, and this is the response of the system. Again, it's just some change in the X, right? And barely any oscillation. There is a little bit of oscillation here, and then going back to 0, okay? So really, that's how the system behaves if it's given something like a bump. And here you can double click on this and look at the ramp behavior, right? So here is the ramp behavior that I just explained to you, right? So you can see the rectangular pulse, triangular pulse, bump. You can see a ramp here, or you can see anything you want. Just connect one of these two wires to it, either this one or this one. Okay, they should go here, and you can get what you want. Okay, so you don't need to cut one wire and connect the other one. I added a third switch. So now if you double click on this one, the bottom signals will go through, and depending on which one of these the ramp goes through or the bump, if you double click on here, now one of the two top signals is going to go through. Again, you can double click on this to get the rectangular pulse, or double click back to get the triangular pulse. Okay, so now by adding these 3 manual switches, you have to pick from these 4 different inputs, and you get to see any of these signals along with the output of the system. I am going to give you a download link under video description so you can play with this and learn from it. Okay? One last thing I want to mention before I stop the video is many people say you can get the solution by convolution. You can convolve the f of t, right, by what we call the impulse response of the system, which is basically the Laplace inverse of your transfer function. Okay, and transfer function is the function that you have when the initial conditions are 0 and for a custom input. So in this case, your transfer function is simply this. So if you apply Laplace inverse on this, you are going to get a function like h of t. This h of t is called impulse response of the system. So another thing they say is if you want the solution x of t, you can do a convolution between your f of t signal and this h of t. So it is going to be h of t, right, times f of t minus tau d tau, correct? Actually, this is h of tau. And you integrate it, okay, from 0 to t, and by a convolution between h of t and f of t, you can get the solution as well. But typically carrying this convolution is you need to be good at integration. But remember that the convolution is the same as saying Laplace inverse of f of s times h of s, which in this case is simply x of s. Okay, so carrying the Laplace inverse is the same as performing the convolution of the input with the impulse response of the system. You can do that as well, but to me, the simplest thing is Laplace transform and inverse Laplace transform. The only thing you need to be good at is partial fraction expansion in MATLAB. If you are not good at it, you don't know how to break the signal into these simpler terms, the command in MATLAB, there is a command in MATLAB which can break down the signal for you. That command is called residue. If you don't know how to work with it, look it up. You can also find it under my controls playlist. I explain partial fraction expansion. Under the same video for Laplace transform, I performed residue command and I showed how to perform partial fraction expansion. So hopefully everything was useful to you. I'll see you in the next lecture. Thank you.